And I like to start doing reviews by talking about sort of two things you should do. And the first thing is to do problems. We're going to do some today. The more problems that you do, the better that you get. Well, first off, you get better in two ways. You get better at doing the algebra and arithmetic, and oftentimes that's what messes people up when it comes to their scores. But the other thing that happens when you do problems is you start to recognize patterns. You're like, oh, I've seen a problem like this before, and when I saw that problem, this was the right method to use. Well, let me use that method again. It will probably work. Oftentimes it does. So that's why you want to do problems. You want to learn to do pattern recognition. And the more problems that you do, the easier it is to spot the patterns. The other thing is to take care of your health. I know that exams are stressful, but you need to make sure that you're taking care of your physical health, getting enough sleep. It's not the best idea to stay up and pull several all-nighters in a row studying, to only show up to the exam and fall asleep. We've had people do that. It's a very bold strategy. It very rarely works. So get sleep, eat good food, go outside, take the occasional walk, whatever you need to do. And also, of course, your mental health. You know, if you need to go scream into a pillow, that's okay. Go scream into a pillow. Whatever it takes for you to go into the exam, you want to be at your best place when you start the exam. Now, by the end of the exam, you might not be in your best place anymore, but at the start, you want to be in your best place. So let's go. I think we only have 12 problems. It shouldn't take too long. Number 1, a limit problem. Find the limit as x approaches 1 of the square root of x plus 3 minus 2 over x squared plus 3x minus 4. Now you should anticipate at some point in this exam limits will show up. So you want to make sure you know how to handle them. Now the first thing you should do if you have a limit of this form, in other words, it's just a straightforward function, you should always say, well, what happens at 1? So what we do is we say, all right, let's plug in 1. Upstairs you get the square root of 4 minus 2, and downstairs you get 1 plus 3 minus 4, which becomes 0 over 0. So that's what's happening currently with this expression. Now when you see 0 over 0, what does that signal? Yeah, 0 over 0 is a signal that you need to do more work. And by more work, what we mean is you need to find a way to rewrite the expression. And so that's what we mean. It's like, okay, so if there was trig functions, we'd find a way, let's use some trig identities. Here, there's no trig functions, it's all algebra. So we think about ways to use algebra. Now for algebra, almost always you think of a couple of basic things. You've got your factoring, and you can also sometimes expand. Sometimes we call that FOIL. The other thing we look for is conjugates. And this is going to be useful if you ever see a square root. So if you see a square root, that's a good time to bring out the conjugate, because conjugates are built for square roots. Now, in this case, we're actually going to use both things. For instance, downstairs, x squared plus 3x minus 4, does that factor? The answer? Yes. Good. Now, we know it has to factor before we've done anything at all. Now, you might say, how do we know that? Well, notice when you plugged in 1, you got 0, which means that 1 is a root. So if 1 is a root, that says that one of your factors has to be x minus the root. So in our case, x minus 1, which makes factoring this really fast, because if I need to get to x squared, the other term has to start with x, and if I need to get to minus 4, it has to be a plus 4. So that's that factoring. All right, well, let us work. So we're going to say this is the limit as x approaches 1, the square root of x plus 3 minus 2, and since we factored, we'll go ahead and write the factoring. Now, in all the problems that involve limits, and we'll say this again, because we will do more limit problems, oftentimes our goal is to get cancellation. Currently we have 0 over 0. In some sense, we can think of this x minus 1 as what's causing our 0 downstairs. So we want to somehow find a way to get an x minus 1 upstairs to get cancellation. So Now we pull out our other tool, conjugation. So you come up, there's a square root there, and to conjugate means that we're going to multiply by a similar expression, except we change the sign in the middle. So square root of x plus 3 plus 2. And this is built off of the fact that if I have a minus b, and I multiply it by a plus b, it becomes a squared minus b squared. So that's what conjugation is based off of. Now, we're still have our limit. So we write that down again. Downstairs, well, notice, where's the conjugation helpful? The conjugation is helpful upstairs. That's where we're pulling the conjugation in. Downstairs, it's not helpful. So here's a good thing to do. Wherever it's not being used, don't multiply out. So downstairs, we're not going to multiply that square root of x plus 3 plus 2 out. So we're just going to leave it as just a new term downstairs. Now upstairs, we're going to multiply it out. And so what do we get upstairs? We're going to get x plus 3, and then minus 4. Now x plus 3 minus 4, what else is that? Or what's another way to write that? Yeah, this is really x minus 1. And lo and behold, see this x minus 1, and that x minus 1, that's what's now causing our 0 over 0. And we can cancel them because we're not at 1. And so that's the key. Get to a point where you can cancel it. And if you're not getting cancellation, something has gone wrong. All right, so 1 over x plus 4 times the square root of x plus 3 plus 2. And now there's no problems. Plug in 1. So we plug in 1. 1 over 1 plus 4. And then we have the square root of 1 plus 3 plus 2. Well, 1 plus 4 is, of course, 5. And that's the square root of 2 plus 2, which is 4. So we end up with 1/20. And that's the answer. Now, I want to note something, because oftentimes we see this happening, especially with people who aren't very practiced with limits, which is they forget to keep writing down the limits. They oftentimes, they do the right manipulations, but they keep forgetting to write the limit down, or they might write it down in the wrong place, where I would say limit as x approaches 1 equals something. That's a notational thing, and we do take off some points sometimes for notation. So just good notation, and good notation is really important. The further you go in calculus and math and in problem solving in general, the more important it is to be careful with your notation. So just get into good habits. It's good to start when you're young, at the beginning of your calculus careers. All right. A question, yes?
Yeah, I apologize, but how did you go from x plus 3 minus 4 to x minus 1?
Well, it's just you add, right? Add 3, subtract 4. So you can drop the parenthesis there. All right. Number 2. A long word problem. Well, sometimes it's the case that the longer the word problem is, the easier it is to do. And sometimes it's not. Well, let's see what we're in this time. So you're preparing a report on sales figures for your business ventures, and you find that you have misplaced information on the actual data. Well, that's not good. However, you do have the following 3 pieces from a different report. Over the course of the first 6 months, and that means from time 0 to 6, the average rate of change for sales per month was 30 units per month. Over the course of the last 6 months, which is from time 6 to 12, the average rate of change for sales per month was 20 units per month. And there were 16 times more units sold at the end, which corresponds to t equals 12, than at the beginning, t equals 0. Determine how many units were sold at the end of the year. Okay. Now, reading this problem, I claim that there's sort of a big signal in this problem. There's a key phrase that's going to tell us what to do. What's our key phrase? Yes, whenever you see the phrase average rate of change, you say, aha, I know what this problem is. it's an average rate of change problem. Now, what is an average rate of change problem? Well, the average rate of change is the following. So average rate of change, say, of some function, let's say f of x, for a less than or equal to x less than or equal to b, is equal to f of b minus f of a. Divide that by b minus a. So if you see any problem that has the phrase average rate of change, write this formula down, because that problem will be solved using this formula. We say, okay, good. We know what the right formula we need to be using is. So let's think about what we have. Well, we don't have an explicit function, but what we can do is we can say that we can make a function. We'll call f of, I'll use t now. It doesn't really matter what symbol we use. This is equal to our cells at the tth month. We can think of it in that way. So now we say, well, let's think about what a becomes. So I have that the average rate of change was 30. So was or is really means it equals 30. So it says our average rate of change is equal to 30. And now I just need to know the times. In other words, the b and the a. And that's given 0 and 6. So part A, that statement becomes that f of 6 minus f of 0 divided by 6 minus 0 is equal to 30. So in other words, I took the average rate of change formula, just plugged in my information, and said, okay, what does it equal? It equals 30. Now, what does this tell us? Well, among other things, if I just cleared the denominator, it says that f of 6 minus f of 0 is 180. All right, so that might come into play later on. Now, we don't know what f of 6 are or what f of 0 is, but now we know what the difference is. Now we go to part B. What does part B say? It's a similar statement. The only thing that changes from part A to part B is the time period and, of course, the value. So now it's 12 and 6, so f of 12 minus f of 6 over 12 minus 6, and it's equal to 20. Well, again, we can clear our denominators, and what can we say? Well, we can say that f of 12 minus f of 6 is equal to 120. So that's the difference in cells at the end versus the halfway point of the year. And now the last thing we have, let's think about C, because C is not an average rate of change. But it says there were 16 times more sold at the end than at the beginning. So what formula does that become? So that's the tricky one. Or maybe it's not the tricky one. 16 times more at the end than at the beginning. What does that translate to?
16 t of 0 equals t of 4?
Yeah, so in other words, if I take the amount sold at the beginning, which is what happens when you plug in 0, multiply that by 16, that's equal to the amount at the end. Okay, so this is what we oftentimes do. When oftentimes we see sentences, we're like, the sentences, that's not why we signed up for math. We want equations and numbers. So we're translating these into formulas. And now we say, wow, look at all these formulas. We can start doing things like combining. So for instance, let's look at these two from A and B. Is there a nice way we can combine these two?
System of equations.
Yeah, we have a system of equations, and we can do all sorts of things. Let's do the following. Let's just add them together. If we add them together, notice what happens. The f of 6's do what? Cancel. So you get that f of 12 minus f of 0 is equal to 300. And now we can say, hey, you know what? We can replace, if we want, f of 12 by 16 f of 0. So 16 times f of 0 minus f of 0 is equal to 300. And now we feel pretty good. We say, okay, that's really like 15 times f of 0 equals 300. Or that says the amount we sold at the beginning of the year, we have to divide by 15. But, all right, these are nice numbers. 300 divided by 15 is 20. Okay, so good. We finally know how much we sold at the beginning, but we don't want to know the beginning, we want to know the end. Well, that's not so bad, because we go back and say multiply by 16, and that gives us the end. So the amount sold would be 16 times 20, which equals 320 units. And that's the answer. Now, I don't know what units are, but that's all right. We weren't told. Okay, good. Good. Yes?
Where did the 180 and the 120 come from?
The 180 and the 120. Well, it came from, oftentimes, see, this is a personal weakness of mine. I struggle. I don't like fractions. And so here, you see on this equation, you have f of 6 minus f of 0 over 6 equals 30. And I say, well, I don't like the fraction downstairs, so I'm going to multiply the 6 across. So the 6 times the 30 is where we got the 180. And the same idea here. We multiply by 6 again. So that's where it came from. All right. Cool. Number 3. Use a limit definition to find the derivative of t divided by t squared plus 1. Now, we can't tell you what's on the exam. However, historically speaking, on 100% of Calc 1 first exams, there is always a problem that states use the limit definition to find the derivative. Now that's 100% up to this point in time. Is it going to continue? I can't officially say, but I'm feeling pretty good that the odds are in our favor that you're going to see a problem like this. So be prepared. Be prepared. So now we're like, okay, we should anticipate this. So how do we do these problems? Well, first off, it says use a limit definition. Now there's actually 2 limit definitions, and you can use either one. So what are they? Well, here our variable is t. It doesn't matter whether our variable is x or t. So one is to say it's the limit as h goes to 0 of f of t plus h minus f of t all over h. Or you can say the limit as, say, some other variable, I'll say s, it doesn't really matter. S goes to t of f of s minus f of t divided by s minus t. This one is sort of, you can see, it looks like the average rate of change because it is the average rate of change. It's the average rate of change, but now you take the limit, and in the limit, the average rate of change becomes the instantaneous rate of change, which is another name for the derivative. Now, both of these are limit definitions, and they both work. That being said, use this one. All right? Now, why do I point to that one? The reason I point to that one is it's really much simpler to work with that in the following sense. Your ultimate goal is you're going to have to be faced with how do I get some cancellation going? And here you say, okay, all I have to do is find some way to get an h and squeeze it out of this f of t plus h minus f of t. Whereas down here, it's like, okay, I somehow have to come up with a way to get an s minus t out. It's a lot easier to figure out how to pull out a single h than it is to pull out the expression s minus t. So that's why I strongly encourage you, if you're going to use a limit definition, use that limit definition. So here we go. Here's what will happen. And this one, by the way, is probably slightly on the more challenging side. We're going to give you something, well, we might give you something a little bit more straightforward. But I figure, we should try slightly more challenging. And then when we get there, we'll be like, okay, I got this, no problem. So I recommend just start by literally writing down the definition. Limit as h goes to 0, f of t plus h minus f of t all over h. Just doing that oftentimes will get you a couple points. All right, so we got our couple points. We're feeling pretty good. But, maybe we got 2. We want 10. Our goal, got to get all the points. Got to get them all. So now comes perhaps the trickiest part. Well, other than the algebra, which is to remember, what does it mean to say t plus h being plugged in? It means you take your expression, and everywhere where you see a t, it becomes t plus h. So it's going to become t plus h on the top. Divide that by t plus h squared plus 1. So that's f of t plus h. Then subtract t over t squared plus 1, and all that divided by h. Now from this point on, the most of the problem that's going to happen from here is algebra. So you got to think about your algebra tools. So we have things like use conjugates if there's a square root, factor and expand. And here, what else do we have? On this one, we get to add fractions. Good stuff. But all those things are algebra. And so we're just going to work through it very patiently. Limit as h goes to 0. This h here, I'm going to write that as a 1 over h. So I don't like fractions within fractions. So I'm just going to write that h downstairs as a 1 over h. Now I want to add 2 different fractions together. What's our right technique? What's the right tool to be using? Yeah, well, common denominator, right? And the common denominator will be what would happen if we multiplied these 2 things together. So in the first case, I need to multiply by t squared plus 1 over t squared plus 1. So I get t plus h times t squared plus 1. Okay, so that's common denominator. I'll write it down here. T plus h quantity squared plus 1 times t squared plus 1. And then I'm going to subtract. Now I'm going to have t times this denominator, t plus h squared plus 1. Let's see, do I have enough fractions? Yeah, there we go. Just checking my parenthesis counts. Parentheses are useful. They oftentimes save points. So get into the habit of using them. They can save your points. All right. So mostly we've just said common denominator, add them together. Let's do a little quick computation here on the side. Whoops, wanted to change color. T plus h quantity squared would be what? So if I square that t plus h.
T squared plus h squared plus 2th.
T squared. Usually we put the 2th in the middle, but you can put it in any order. We're adaptable. We've seen many things. All right. So what do we have? We have the limit as h goes to 0, a 1 over h, and then we're not really doing anything with the downstairs. If it's usually, you don't want to expand what's downstairs. It's not going to help you, and you're likely to make algebra mistakes. We don't want to make algebra mistakes. We want to keep it nice and simple. Now we do our foiling. So we multiply t plus h by t squared plus 1. So we get t cubed plus t plus h times t squared and plus h. And now we multiply this minus t through. Now remember, there's this minus sign, so carry it to every term, not just to the first term. So it'd be minus t cubed minus 2 times t squared h minus th squared and minus a t. All right. Now, what should be true at this point? Well, we should at some point get to the point where we can cancel an h. If you've lived a good, clean algebra life, then nice things will happen. Well, what are nice things? There's a t cubed. That doesn't have an h. But there's a minus t cubed. Those cancel. This plus t, there's no h there. But there's a minus t on the end. And those cancel. So everything without an h is canceling off. Everything that's left has an h. There's an h t squared, there's a single h, there's a 2t squared h, there's a th squared. So all those things that are left have h's in them. So what we can do is we can factor an h out, and I'll just go ahead and do that. So I'm going to pull an h out of the top, so I have h over h, and then what do I have left? On the top I have t squared plus 1 minus 2t squared. Oh, I could have combined those together. Well, all right, we'll do that in a second. And then minus t times h. And then the downstairs is still the same. T plus h squared plus 1 times t squared plus 1. And now, of course, we get to the point of having the h's cancel. That's our goal. Our goal is to get the h's to cancel. So if they're not canceling, we've got to go back and check our arithmetic. So now, we've gotten the h's to cancel. What do we do from here? What's the next step?
Plug 0 for h.
Yeah, we evaluate. Because now we're not getting the 0 over 0. That's what was causing, see the h down here, that was causing the 0 in our denominator. We've canceled it off, so we're no longer 0 over 0. So we say, okay, what do we have? Well, upstairs we have t squared plus 1 minus 2t squared, and that'll be 0. So I'll go ahead and put those two together to get 1 minus t squared. And downstairs we get t squared plus 1, another t squared plus 1, which becomes t squared plus 1 squared. And we circle our answer. Okay, good. Now, this problem doesn't ask, but if we wanted to be extra sure we got the right answer, what could we do at this stage? We can actually take the derivative using better tools. So even if it doesn't say take the derivative using better tools, it's like you should always double check. So let's do a quick double check. So derivative t over t squared plus 1. What rule do you need to take this derivative? It's a quotient rule. So this says you take the bottom term, t squared plus 1, times the derivative of the top, 1. Then you're going to subtract the top, which is t, times the derivative of the bottom, which is 2t. And you're going to divide all that by the bottom term squared. Well, we have a t squared and a minus 2t squared, and there's a plus 1. Put that together, you get 1 minus t squared in the numerator, and t squared plus 1 quantity squared in the denominator. And lo and behold, these match, which makes us happy. Woohoo! That's a sign that we probably did it right. And now, you look at this and say, why do we bother with the quotient rule? This is so simple. No. Clearly, hopefully one of the things you've realized by now is that limits, they work, but they're not fun. So avoid them if you can. That's what we've learned. Okay, number 4. Find all asymptotes for the following functions. Following function. So this is a piecewise function. So I have two things coming together. Now when we talk about asymptotes, there's two kinds of asymptotes. There's the vertical variety, and usually when you have a vertical variety, there's somehow a division by 0 going on. So it's like I have my denominator is 0, so we should just do a quick check and see if we have any of those. And then there's the horizontal variety, and in the horizontal variety, we say what happens as you go towards an infinity. And there's actually two types of infinity. There's a positive infinity and a negative infinity. So those are the things we look for. So let's just check if we have any vertical asymptotes. So let's start. Interesting. Okay. Well, if I have a vertical asymptote, what should I be looking for? Yeah. Do I ever divide by a 0? Okay. Well, let's see. 3x plus 5. Could that ever be 0? Well, 3x would equal negative 5, x could equal negative 5/3. Okay, so what does that say? Well, it says, yeah, it's possible. It's possible that we could have an asymptote. So yes, we're going to have a vertical asymptote. Because the other thing to check is, what do you get when you plug in negative 5/3 upstairs? Well, if it's not 0, then there's definitely a vertical asymptote. If it is 0, then what happens then? Well, then you get to do more work. Okay, but if it was an if you can just ask yourself the question, if I plug in negative 5/3, would I get 0 out? Well, you'd get 5 minus 10, and then plus 4 times something big, and no, that's not 0. So yeah, so we have a vertical asymptote happens at x equals negative 5/3. Okay, how about here? We should check that. 3 minus 5 e to the x. Well, that says what? 3 minus 5 e to the x equals 0. Or 5 e to the x equals 3. Or e to the x equals 3/5. Well, can e to the x equals 3/5? Well, you can get the x out. You could say, how do you get the x out of the exponent? Natural log. Okay, so is that a vertical asymptote? Log of 3/5.
Should it be negative 3?
Well, so it depends on how you do the arrangement. So I did something kind of strange. I moved the minus 5 e to the x across, and you could have moved the 3 across, and you'd have negative 5 e to the x equals negative 3, and then you'd have negative 3 negative fifths. Now, is this a vertical asymptote? And why not? This one, you have to think a little bit. There's a little subtlety here, but I just want to point the little subtlety out so that should you encounter subtlety in the future, you're like, yeah, I've seen subtlety before. I can handle subtlety. Okay, I'll tell you it's not a vertical asymptote.
Oh, is it because it's a natural log?
No, it's okay that it's a natural log. It's not necessarily just because it's a natural log, but there is something about the number. So if you think about e to the x, and I'm sure you often do, you're often laying in bed thinking, no, I want to think about e to the x a little bit, because it's such a beautiful function. A whole lot of mathematics says, life is good because e to the x is so clean. So this is the graph of e to the x. And notice, what do we care about? There's this constraint here that says x is above 0. So that says I only care about this part of e to the x, what's on that side. I don't care about what's over here. What's e to the 0? It's 1. So e to the x is going to be at least 1 when x is above 0. But what's true about 3/5? It's below 1. That says that this number, log of 3/5, it's actually a negative number. So, it is true that if there were no restriction put on the x, there would be a potential asymptote. But because there's restriction put on x, where the asymptote occurs is outside the restriction. So that's okay. That's okay. No problem.
Can you explain that again?
Sure. So we have a piecewise function. So I don't know exactly what it looks like, but let me make up something. And then I'll sort of explain. So let's suppose this e to the x plus 9 over 3 minus 5 e to the x it's doing some sort of behavior, and I don't know. And then I'm going to put it the sort of dashed thing in. Oh, here. Oh, there. Okay, I've messed up my picture already. Let me try again with a new clean piece of paper. Okay. So whatever this function is doing, we know that there's this asymptote here. So this function is doing something, and it blows up, and maybe it's doing something here. So that's this part. And now there's this other function up on top, which is also doing something. I know that's not very descriptive to say it's also doing something. But again, who knows what it's doing. And it has an asymptote over here. And again, I'm just making stuff up. Okay. All right. So these are the two functions. And what we're trying to do is we're saying we're going to make a piecewise function. And so individually, it's true that both pieces have asymptotes. So this piece has an asymptote, and that piece has an asymptote. But now when you put them together, you say, all right, what I'll do is I'm going to follow the purple part only for positive x. So that says I'm coming along this stretch. And then I'm going to follow the green part for the rest. So what's happening is that even though that there is an asymptote on the purple part, the part that I'm keeping doesn't have an asymptote. So it's not an asymptote for the function that's been defined piecewise. So that's what's going on. Okay. All right. Well, that was the vertical, which became more subtle than I wanted it to be. Oh, well. Horizontal, right? We still get to do that. So, horizontal. Now, horizontal, that's nice because you know exactly what you're going to do. So, we'll take the limit as x goes to infinity of f of x, and let's work on that one. So, as I'm getting close to infinity, which variation of the function do I work with? The top one or the bottom one? The bottom one, because I'm going to plus infinity. Well, that's above 0. So this becomes the limit as I go towards infinity of e to the x plus 9 over 3 minus 5 e to the x. Now, what happens as you go to infinity? Well, you get big number over big number. All right, that's a problem. So how do we handle it? So, what do we do? What do we do?
What if you multiplied both the top and the bottom by 1 over e to the x?
Okay, so we have a good idea. Multiply top and bottom by 1 over e to the x. So here's the idea. If you're going to a big number over big number, you ask yourself the question, what's making it big? And the answer is the e to the x. So it's like, all right, time to slow it down. We're going to slow it down, and we're going to slow it down by just the right amount. And what's just the right amount? We're going to slow it down by something which would cancel out the growth of the biggest piece. And since the biggest thing is growing like e to the x, we divide by e to the x. So this becomes the limit as x goes to infinity. And upstairs we're going to get 1 plus 9 over e to the x. And downstairs we're going to get 3 over e to the x minus 5. So it's still the same function, we've just chosen to write it in a slightly different way. Now we ask ourselves the question again, what happens as x goes to infinity? Well, anything divided by e to the x, what's that going to do? Goes to 0. So we get 1 over negative 5, which is negative 1/5. Okay, so that says, and oftentimes you write this as y equals negative 1/5. So there's a horizontal one. I guess I should have said there's a vertical one. All right. Are we done? No, why not? Negative infinity, right. Good. So limit as we go towards negative infinity of f of x. So now we're in the different part of the function. So we have to use a different piece. Limit as x goes to negative infinity of the square root of 5 plus 6x plus 4x squared divided by 3x plus 5.
Why do we use the top function for when we decide to go x to negative infinity?
Well, because you want to say which piece are you in. So if you come back to the picture, remember how we split our function into two parts? We said, well, on one side, we're going to use one part of the function. On the other side, we're going to use the other part of the function. And so we just have to decide which side are we on. So in our case, as we're heading towards negative infinity, well, negative infinity is negative. So we want to use the part of the function which is defined for the negative numbers. So that's why we're using that part of the function. All right. So again, big number over big number. What do we need to divide by? What's our growth? X. It looks like X, right? It's easy to see downstairs. See, it's the X. That's causing our growth challenges. So 1 over X and 1 over X. So that's the limit. As X tends to infinity, downstairs, pretty easy. 3 plus 5 over X. Good. That'll be easy to work with. Upstairs, what do we want to do with that 1 over X? Yeah, we want to put it into the square root, right? Good, good. Now, side note. Let's just remind ourselves. Is it true that 1 over the square root of x squared equals 1 over x? And why not? Oh, wait, I'm sorry. We should answer the first question. Are these the same? No, there's a subtle difference. It's very subtle. What's the problem? The minus sign. See, 1 over the square root of x squared, you've lost your sign. So if x is positive, they are in fact exactly equal. If x is negative, what's the difference? You're off by a sign. So you have to be careful here. So this is yes for above 0 and no for below 0. So just be careful. So when you get rid of things, really what you really have here, 1 over the square root of x squared is really like 1 over absolute value of x. So remember, if you deal with an absolute value of x, there's two possibilities. If you're above 0, it's like positive. And if you're below 0, it's like negative. So be careful. Be careful. So what will happen here is that we'll replace, where do we have space? We'll do it here. We have this 5 plus 6x plus 4x squared. And this 1 over x will become a minus 1 over the square root of x squared. And we know we're negative because we're heading towards negative infinity. So we can assume what we're negative values. So there's a minus sign that's going to be introduced. So I'll put that in front. Minus. And then we can put the two square roots together. So it'll become 5 over x squared plus 6x over x squared plus 4x squared over x squared. Well, now I think we can take our limit. Because, of course, the x squared over x squared cancels on the inside. X over x squared becomes 1 over x. So what happens in the limit? What do we get? Well, inside the square root, what's going to happen? That'll go to 0. That'll go to 0. And what does the 4 do?
It'll remain in the square root.
Yeah, it's just like, I'm pretty happy with my 4-ness. I'm pretty comfortable where I'm at. I'm going to stay 4. So we have a square root of 4, also known as 2. Downstairs, what do we get? 3. So we put it together, we get negative 2 over 3. And again, we usually like to think of horizontal asymptotes as, what does it approach? So we think of y equals negative 2/3. So there's 1 vertical, 2 horizontal. All right. Good. All right. Well, let's try the next one. Number 5. Let y equal 3x plus 2 be the tangent line to y equals f of x at x equals 1, and y equals 5x minus 7 be the tangent line to y equals g of x at x equals 1. Find the tangent lines to the following functions. Now, this problem is basically built off of the following principle. Do we understand what tangent lines are? Now, there's lots of ways to think about tangent lines, but in particular, what's trying to go on here is that there's this philosophy, which is the following. There is the tangent line at a particular point, so 2f of x at x equals a. And now there's the other thing is there's this two pieces of information, namely what is the function at a and what's the derivative at a. So it turns out that there's more or less these two things are equivalent. If I know the tangent line to my function at a point, I know what the value of the function is at that point, and I know what the derivative of that function is at that point. Now, the reason we know the value of the function comes from the word tangent, because the tangent line touches the function there. And that's what tangent means, to touch. The reason we know the derivative is because the derivative measures the instantaneous rate of change, and that's what's being captured in the slope. And of course, if we have these two pieces of information, we can write down the formula for the tangent line. So this is the formula that y minus f of a is equal to f prime of a times x minus a. So what we're going to do is we're going to take the information given to us. We're going to do a conversion into saying, what do we know about the function f and the function g? We're going to use that information with these pieces, and then we're going to find our new tangent lines. So let's start by first off writing down what we know. So we have y equals 3x plus 2 is tangent to f of x at x equals 1. So what does that tell us about f at 1? So what we do is we come and we plug in 1. What do we get? 5. So f at 1 is equal to 5. What about f prime of 1? We read off the slope. It's 3. So from the tangent line, we grab the two pieces of information about f. F of 1 equals 5. F prime of 1 equals 3. Okay. Now, we do the other one. We have y equals 5x minus 7 is tangent to g of x at 1. So what is g of 1? Negative 2, because we can plug 1 in. 5 minus 7 is negative 2. And what is g prime of 1? It's 5. So really, we could take the statements that were given to us and we'll say, let us translate into, here's what we know about f and g at the point 1. Now we say, okay, let's go through and work these one at a time. So let's do part A. So here we have this function f of x, g of x. So what we need to know is we need to know the following. We need to know what is f of x, g of x, evaluated at x equals 1. And we need to know what's the derivative of f of x, g of x, evaluated at x equals 1. That's what we need to know. Well, let's start with f of x, g of x. Really, this says just plug in 1. F of 1, g of 1. F of 1 times g of 1 will give us negative 10, because you just, f of 1 is 5, g of 1 is negative 2. Now, how do we do the derivative? So I want to figure out what is f of x times g of x evaluated, the derivative of that evaluated at 1. So what's the first thing we need to do? So I want to take the derivative of these functions and evaluate it at 1. So what we need to do is take the derivative of these functions. If I have f of x over g of x, what rule do I need to take that derivative? It's a product rule, because there's two things multiplying. The quotient rule will come up in part B. So product rule. So in some sense, this question is testing several concepts. It's testing, all right, do we understand tangent lines? It's also testing, do we know our rules for derivatives? So I like to write this as f prime of x times g of x plus f of x, g prime of x. So whenever you're taking a product, you say, look, everybody gets its turn. First off, f, it's your turn. you're going to be the derivative. Everybody else has to wait. And now g, okay, you get to do it in round 2. And it's the same for like the triple product rule, right? That was one of the quiz problems. F of x times g of x times h of x. All right, so what do? Well, we plug this in. Plug in 1. F prime of 1 times g of 1 plus f of 1 times g prime of 1. Well, let's see. F prime of 1? 3. G of 1? Negative 2. F of 1? 5. G prime of 1? Still 5. So 3 minus 2, negative 6. 5 times 5 is 25, which 25 minus 6 is 19. Now we're not done yet. Well, what we've done is we said, okay, we have this function. We now know what the value is at 1. And we also know, it didn't explicitly state. It should have said, find the tangent lines at 1, which is the only place we could have. We now know what the value is at 1. We now know what the slope is at 1. The last thing to do is write down the line. So we use our formula. So we would say y minus 10 is equal to, so y minus the y value is equal to the derivative, 19, times x minus our x value. And now we're done. We could leave it like this, or if we wanted to, we could work it out. That says y equals 19x, then you have a minus 19. Bring that across would be a minus 10, so minus 29. And that's the answer for part A. But once you know part A, part B and C are going to be very similar, so we can go through those a little bit faster. All right. One thing you could do is, if you wanted to, just to keep your sanity, you could say, well, let's let h of x, we'll just make the name for a new function. We'll call it g of x over f of x. And then I want to say, well, h of 1, that would be g of 1 over f of 1, which would be negative 2 over 5, negative 2/5. And that finds our function at 1. Then we say, all right, next step is take the derivative, because eventually I want to take the derivative at 1. So an intermediate step that helps us is to say, well, what is the derivative? So we say h prime of x, use the quotient rule. So you take the bottom times the root of the top minus the top times the root of the bottom, all over the bottom squared. Now I will say, one of the things that we do is we kind of know what conventions you're used to. So a lot of people memorize f of x over g of x for the quotient rule. And then we're like, okay, well, can you handle if we switch the names? Well, hopefully, yes, I hope. So be careful, be careful. We know what you know, but now you know that we know what you know. You know, and of course, it just keeps going. It's a beautiful feedback. Okay, so plug in 1. H prime of 1. That's f of 1 times g prime of 1 minus g of 1 times f prime of 1. All divided by f at 1 squared. Okay, well, it's going to be something. Well, it almost always is something. It frequently happens. So, what do we have? We have f of 1 is 5, and g prime of 1 is also 5. Subtract g of 1, negative 2, and f prime of 1 is 3. And all that's divided by f of 1 squared, so 5 squared. So it becomes 25 plus 6, which is 31/25. Okay, well, now what? Well, we have our value of our function. We have our slope of our function. So we say y minus our y value is equal to our slope, 31/25, times x minus our x value. And we're at 1. And now, that looks terrible. And we weren't told we have to simplify, so we're not going to. And so we're just going to stop there. In fact, that's one of the rules. says, look, if a problem doesn't say you have to simplify, you don't need to. If it does, then you better do it. I mean, it's not algebra we're testing you on. It's calculus. So well, of course, it feels like we're testing you on algebra with all the algebra stuff we end up doing. But, we want you to make sure you can do the calculus part. All right, part C, f of x to the fourth minus g of x squared. What's the rule we need here? What? The chain rule, yes. And how can you spot that it's the chain rule?
Since x sub 4, we're doing something to that x.
Right. So it's this function x to the fourth inside the function f. And over here it's the function x squared inside the function g. The chain rule is one of the best and most powerful tools that you have. So you should get very comfortable working with the chain rule. Like you and the chain rule should become on a first name basis. You can just call it Chain. Hey Chain, how you doing? Great to see you. Let's work together and get some good points on this calculus test. All right. So first off, we'll figure out h of 1. Well, that's what you plug in 1. So you get f of 1 to the fourth, which is 1, minus g of 1 to the fourth, which is 1. All right. Well, f of 1 is 5. Then we're going to subtract g of 1. So that's minus 2, which means we're getting 7. So there's h of 1. h of 1 is 7. h prime of 1. Okay, let's test your chain rule knowledge. So, what is it? What do you get? Sorry, what? Okay, the derivative of f. X to the fourth states you don't change for the inside. What else do you need? 4x cubed on the outside. So remember, the chain rule says take the derivative of the outside, leave the inside as is, nice and pristine. Then multiply by the derivative of the inside. Okay, that's half of it. What's the other half?
G of x squared.
Well, g prime of x squared, right? Times 2x. Whoops, I said h prime 1. That should be h prime of x. My apologies. There we go. That's a very badly written x now. So, what is h prime of 1? Well, it'll be f prime of 1 times 4 minus g prime of 1 times 2. So, f prime of 1 is 3. So, we get 3 times 4, which is 12. And g prime of 1 is 5. 5 times 2 is 10. 12 minus 10 gives us 2. So that's our slope, 2. That's the value of the function, 7. So in other words, we have these two pieces of information, value of the function, value of the slope, which means we can get our tangent line. So y minus our function value, which is 7, is equal to our slope, 2 times x minus where we're going at. We're currently working at 1. And this one we could simplify, and why not? We should practice simplifying. So y equals 2x, then it would be minus 2, but you'd add 7, so that makes it 2x plus 5. And there's our answer. Oh, good. We fit on one page. Barely. But we made it. We made it. Okay. Number 6. Use the limit definition of the derivative to find f prime of x, where f of x equals 3x plus 4 root x. Aha. The limit definition. Good. So we've seen one of these before, so we should be pretty comfortable. So let's just see where we end up. Okay. So we say, look, we're looking for f prime of x. We write down the definition. And again, I strongly encourage you to use the h variation. H going to 0, f of x plus h minus f of x all over h. Well, this becomes the limit as h goes to 0. And now, the f of x plus h, that's where you've got to be careful. Everything that has an x becomes an x plus h. So 3 times x plus h plus 4 square root x plus h. And then we're going to subtract 3x plus 4 square root of x. All that divided by h. Now, one of the things I want to point out, this is an advanced technique that saves points. It's called parentheses. And so if you use parentheses, you're less likely to make mistakes with signs. And you're probably like, well, how much could that hurt me? At some point, you're going to get stuck and you're going to be frustrated, like, where did I make my mistake? Because I feel confident I did everything correct. And you won't think about, oh, wait a second, there should have been parentheses here the whole time. So in other words, this minus goes through and affects that term as well. So it's good habit to get into using parentheses when you should. And the sooner you start developing your good habits, the better off you'll be. All right, well, that doesn't look too terrible. Let's see where we go. Limit as h goes to 0. Expand it out. We get 3x plus 3h plus 4. And what do we do with the square root of x plus h?
Leave it.
Yeah, the answer is still the square root of x plus h. Square roots are a big challenge for us. We are going to be often frustrated with square roots. So minus 3x, and here that minus 4 root x. All that divided by h. Well, what do we have?
The 3x can cancel out.
3x's can cancel out. Good news for us. And there should be lots of cancellation. And now, we're like, hey, square roots are involved, conjugates, but we're also like, there's like 3 terms up here. When we're doing conjugates, how many terms do we want? We want 2 terms, right? And 3 is too many terms. What do we do? Sorry, what? Factor something out of the top. Well, maybe. Now, of course, one of the things you could be saying is, well, I'll drop this problem. No, don't drop this problem. Don't drop the limit problem. My goodness. If you're going to drop a problem, drop number 7. No, don't drop that one either. That's a beautiful problem. I like it. All right. Well, we're going to use advantage. It's the latest craze. It's called plus. Now, all the kids are using it these days. How does plus work? Well, plus works by saying, you know what? I can really break this into 2 parts. So whenever you have addition upstairs, you can break it into 2 parts. See, the 3h, I can think of it as 3h over h. What else is that known as? It's 3. Plus the stuff that's left. So I can pull off the part which is happy to work with, no problems for me. And then I have the stuff that I'm having a hard time with, and that's still left over. Okay. Now, we're a little bit happier. What comes next?
Conjugate.
Yeah, conjugates. Now we're 2 terms. Life is good. We like conjugates. It's not to say that you can't do conjugates when there's 3 terms. It's just things get a little bit messier, especially when there's 2 square roots involved. So, 4. We probably should have pulled out a 4 to begin with. Oh well. Live and learn. 4 square root of x plus h plus 4 square root of x, because we changed the sign in the middle. And 4 square root of x plus h plus 4 square root of x. Okay, that's going to be the limit. H goes to 0. We still have the 3 in the front. And here, well, when we multiply the first 2 terms, so it becomes like a squared minus b squared. The cross terms cancel. So we're going to get 16 times x plus h minus 16 times x. And downstairs, we're going to end up with the h times the 4 square root of x plus h plus 4 square root of x. We don't multiply out downstairs. You only multiply out in the part where the conjugate helps you. Well, 16 times x plus h, I can replace that by 16x plus 16h. And then what happens?
The 16x will cancel.
Right, we need to cancel the 16x's first, but then we can cancel the h's. And now, where are we at? Well, we're at the point where we have limit as h goes to 0. We have 3 plus 16 divided by 4 square root of x plus h plus 4 square root of x. So we canceled the h. And when you've gone to the point where you've canceled the h, you're basically done. What's the last thing to do? Plug in 0. So you get 3 plus 16. Then you get 4 square root of x plus 4 square root of x downstairs. Of course, that would be 8 square root of x. And so you can simplify that. You have 8 square root of x downstairs, 16 upstairs, so you can write that as 2 over square root of x. And it's easy for us to check. This one we can do in our head. Derivative of 3x is in fact 3. 4 square root of x, the way we think of square root of x is x to the 1/2 power. Take that derivative, the half comes down. So that's where the 2 comes from. And then it's x to the negative 1/2, which is a square root of x downstairs. So good. Whew. Looks like we did it right. Again, just be careful with your algebra. Look for, no, don't forget parentheses when you need it. Use conjugation. Be careful with your notation. When you have a limit, make sure you put the limit there. When you're done with the limit, don't put the limit. See, notice how there's a limit here, but not a limit there, because we've actually done the limit. So we look for these things. So, all right. Good. We're halfway done. How you doing? Oh, yes.
So when you put that 3 to the side, what happens to the h?
Well, there was a 3h over h. So what happened was we really kind of had this intermediate step, 3h over h, and then the h is canceled. And that's what happened. All right. I see I'm going a little bit slow. I'll try to talk faster. Well, maybe not. Who knows? Okay, number 7. Find the limit as theta goes to 0 of theta squared sine of 6 theta over 1 minus cosine 4 theta times tangent of 3 theta. This one looks great. Looks like a lot of fun. Now, when you see a problem like this, and you're probably thinking, what do you mean by like this? You see how there's trig and algebra. So in other words, there's like theta and sine of theta being mixed in. Whenever you see a problem that involves limits, and there's both a trig function and some parts which are outside of trig functions, like the theta, you should automatically think of, aha, I have this cool fact. And the cool fact is that the limit as blah goes to 0 of sine of blah over blah equals 1. Yeah. Now you're probably thinking blah does not sound very mathematical. I'm just saying it's something. You have this group. It does. Oftentimes we think of sine of x over x, but it could be like sine of 2x over 2x, or sine of x cubed over x cubed. It's just sine of something over the same something that matches. It goes to 1. Life is good. So that's what we're going to do. We're going to say, look, we want everything as much as possible to look like that. So we're going to think about our pieces. What's another way to think of the tangent function? Yeah, sine over cosine. So this is sine of 3 theta over cosine 3 theta. So we're going to use that, and we'll replace that because we really want to use the sine part of it. And the cosine part we're okay with, because cosine of 0 is 1. Life is good. Now 1 minus cosine 4 theta is going to give us a little bit of consternation. It's going to be a little bit challenging to think of. Because what happens? Well, you get 1 minus 1. Cosine of 0 is 1, which is 0. But of course, 1 minus cosine does not look like sine. Or does it? If we had 1 minus cosine squared, life would be good. It's 1 minus cosine. How can I make a 1 minus cosine into a 1 minus cosine squared? Conjugate, right, conjugate. So let's do a little bit of work on this side. Okay, You're probably thinking, boy, he really loves his conjugates. I do. It's a good tool. Will they be on the test? Maybe. But even if it's not, it's good to know. So that when you walk into the test, you're like, I know. And knowing is half the battle. Okay, so I have that 1 over 1 minus cosine 4 theta. I multiply. I'm not doing anything here. I'm just cleaning up. So this would be 1 plus cosine 4 theta upstairs. And then downstairs, it's 1 minus cosine squared of 4 theta. So it becomes 1 plus cosine of 4 theta. Well, running out of space. Divide that by sine squared of 4 theta. Sorry, it's a little bit cramped. But it's all there. It's all there. So let's update this with the idea to get as many trig functions into sine as we can. This becomes the limit as theta goes to 0. We have a theta squared, a sine of 6 theta. That sine of 6 theta comes from the sine of 6 theta. Downstairs, the tangent of 3 theta, let's tackle that one. There's a sine 3 theta over cosine 3 theta. This cosine 3 theta, we can move it upstairs. So I'll write as cosine 3 theta upstairs. And then I have a sine 3 theta downstairs. So this sine 3 theta and this cosine 3 theta came from the tangent. All right, so I move that up. The 1 over 1 minus cosine 4 theta says you can put a 1 plus cosine of 4 theta upstairs, and then downstairs you've got really a sine squared of 4 theta. Okay. Now, by the way, sine squared of 4 theta you can think of as sine of 4 theta times sine of 4 theta. What's our next step? Yeah. Right. You see how we're going to use the power of the blah. We want to get things that look like this. So, for example, this sine of 6 theta, what do we want to divide by? What do we want underneath this? We want 6 theta. But if I divide by 6 theta, what do I need to do? Also multiply by 6 theta. So this 6 theta and that 6 theta cancel out. So I haven't changed anything. What do I want to divide this sine 3 theta by? By 3 theta. But if I divide by 3 theta, I better multiply by 3 theta downstairs as well. The next term, I want to match what's on the inside. Divide by 4 theta. Multiply by 4 theta. Last one, there's another 4 theta. So divide by 4 theta again and multiply by 4 theta again. Now, let's see what happens with all these thetas. How many thetas do we have upstairs? One, 2, 3. How many do we have downstairs? 1, 2, 3. Which means that all the thetas cancel out. Almost as if whoever wrote this problem had planned for it to happen that way. Because they did. I know, I wrote the problem. I meant for it to happen. I'm actually kind of glad it did, because I was only about 50% sure it would before I started doing this problem. Okay, so let's think. Oh, actually, we don't need to do limits anymore. We're ready. Let's go through it piece by piece. Sine 6 theta over 6 theta. That's our sine of blah over blah. What does this go to? 1. So we have 1. Cosine 3 theta. What does that go to as theta goes to 0? 1, because it goes to cosine of 0, which is 1. 1 plus cosine of 4 theta. What does that go to? Go to 2, because it's 1 plus 1. So it's 1 times 2. Downstairs, the sine of 3 theta over 3 theta goes to 1, because it's sine of blah over blah. Sine of 4 theta over 4 theta still goes to 1. Because, again, the key is the inside of the sine matches what's underneath it. So as long as that's the case, and what's on the inside goes to 1, goes to 0, the whole thing goes to 1. So you get 1 times 1 times 1. And then don't forget these pieces. There's a 3, a 4, and a 4. So what do we have? We have 2 upstairs. Downstairs we have 48. Did I forget something?
6.
Oh yeah, there's a 6. There's a 6 upstairs I forgot. Sorry. There's a 12 upstairs. Downstairs there's a 48. Final answer is 1/4.
Sorry, where did you get the 2 from?
This 2 right here came from the 1 plus cosine 4 theta, because it's the 1 plus 1, because cosine of 0 is 1. All right, good. Whew. 1/4. That works out pretty nicely. Okay, number 8. You are working on a machine that tracks mosquitoes and then shoots them with a high-powered laser. For best effect, the mosquito should be shot while it has no vertical acceleration. So it's not that it's motionless, it's just it's not accelerating. Now, given for time between 0 and 7, the height of the mosquito is given by the equation, and here's this equation, where t is measured in minutes, then determine the times the machine would shoot at the mosquito. Okay, so what do we have? We have a few keywords. Acceleration, and then there's the height, which you can also think of as position. So, what's the relationship between the location and the acceleration? Second derivative. So if I have a location, if I want to get to acceleration, I take 2 derivatives. Good. So this is not such a bad problem. And what do we want? Well, it has no vertical acceleration. What does that tell us about what do we want for the acceleration? 0. Yeah, so what this problem says is, once we read it, it really says, figure out when does the second derivative equal 0. That's what this problem is about. So now it doesn't sound like such a scary problem. Even though there's a lot of words, once we oh, whoops. I don't know why I put 1/4 twice. You only need it once. That was an excessive 1/4 thing there. 1/4 t to the 4th minus 4 t cubed plus 45 halves t squared plus 50t plus 40. All right. Well, we want the second derivative. Oftentimes, to get the second derivative, you should start with the first derivative. It's a natural place to start. What's the first derivative turn out to be? All right. T cubed, and then? Minus 12t squared, and then? All right, 45t, and then? 50, and then? 0. Nice. Second derivative, h double prime of t, would be? 3t squared minus 24t plus 45. And then the 50 goes away. And now, next thing we do, set it equal to 0. Okay, well, now it's solving for t. We have a quadratic. Well, how can we make progress? What should we do?
They take a 3 out.
Yeah, everything has a 3 in it. Let's take the 3 out. T squared minus 8t plus 15 equals 0. And now what? Well, hope it factors. Will it factor? Unusually often things do factor. You're going to leave calculus thinking like, wow, everything factors. Life is good. Well, with one exception this semester. It's a beautiful problem. Oh, I'm really excited. But that's coming in a couple weeks. Okay, so how does this factor? T minus 5 and t minus 3. So you want 2 things that multiply together to give 15. Turns out there aren't that many things that multiply together to give you 15. 3 and 5 do. And they need to add together to negative 8. Well, that's good. Negative 3 and negative 5 do. So what does that say about t? Well,
T equals 5 or T equals...
all right, 3 and 5. Now, question. Do we keep both these answers? Yes. Now, But it's not a trivial question. It's actually, what did we do to make sure we keep both the answers? Because there's something we haven't, you have to go back and check. Namely, it's not just any arbitrary t. It has to be between 0 and 7. So if we had gone like 3 and 9, what would we do? We'd get rid of the 9. We'd only keep the 3. So double check. So sometimes, they have an answer that's slightly outside of the range and doesn't work. So there was a Calc 2 exam a couple weeks ago, and we got about 98% of the students they missed a small detail about that. So they weren't happy. But they learned a valuable lesson. Check. Check. All right. Well, on to number 9. So let f of x equal e to the 3x plus x to the 20th plus 17x to the 15th plus 8,387 plus sine of 3x. And we're asked to find the 20th derivative as a function of x and find the 35th derivative at 0. All right. Now, we can probably guess what we're not going to do. What we're not going to do is actually take 20 derivatives. And we're definitely not going to take 35 derivatives. Instead, what we're going to do is say, let's think about what happens. So let's go through the terms and talk about what happens to the terms. So e to the 3x, what happens when I take derivatives of e to the 3x?
3e to the 3x.
Yeah, when you take one derivative, a 3 comes down. So what ends up happening is you get, for example, the next one will be 3e to the 3x. The one after that will be 9e to the 3x. Or really, I should write this 9 as 3 squared. The next one would be 3 cubed, and so forth. So in particular, if I want to know what happens, I basically say, how many derivatives did I take? That's how many 3's came down. So that term is not so bad. The 8,387, okay, that's just to scare us and make us nervous. But what happens to that?
It's constant.
It's constant. It goes away right away. So that was just there to intimidate us. But it's hard to intimidate us. We will not be intimidated. All right. Now, x to the 20th. Let's think about that. Well, what's the derivative of x to the 20th?
20x to 19.
Yeah, 20x to the 19. And then what's that derivative?
20 times 19, x to the 18.
20 times 19 times x to the 18. And so forth and so on. Now, eventually, what's going to happen is, when you get to the 20th derivative, you're going to get 20 times 19 down to 1, and then it'll be x to the 0. And then after that, what's the next derivative right after that? 0. So that's going to 0 out. Something similar happens here. We'll talk about but we understand how powers of x work. The powers of x, you keep bringing the numbers down, and the numbers keep decreasing. By the way, 20 times 19 times ... times 1, there's a shorthand for that. Do you remember what it is? Yeah, it's like really excited. It's not just 20, it's 20! Woo, 20, yeah! So, no, it's just 20 factorial. That's just notation. Okay. What does that leave us with? It leaves us with the sine of 3x. Now, there's two things that are going to happen. Let's talk about the 3x. Because of that 3x, what will happen every time we take a derivative? We do a chain rule, and it's the same thing that happens with the e to the 3x. We keep getting powers of 3. So there's going to be powers of 3 showing up. So that's what's going to happen because of 3. But what about the sine? Let's sort of work through it. The derivative of sine of 3x would be, there's a 3, and then cosine 3x. Then the next derivative would be 3 squared, and then derivative of cosine, negative sine. And then the next derivative, well, another 3 comes out, and then it's cosine. And they're still negative. And then the next one after that would be a 3 to the 4th, and then it would be, yeah, it would be negative sine, and there's another negative, and we're back to sine of 3x. So what's going to happen is you're going to get powers of 3, but then there's this pattern of you have a plus sine, plus cosine, minus cosine, plus sine, plus cosine, minus sine, minus cosine. So there's this sort of pattern going on with the various pieces. So, this one is testing patterns. Do you spot the patterns? So let's talk about the 20th derivative at x. So we'll go through the terms one by one. So e to the 3x, take 20 derivatives, what will we end up with?
E to the 20.
3 to the 20th, because we took 20 derivatives, and e to the 3x. The x to the 20th, what will we have when we've taken 20 derivatives?
20 factorial.
That's the 20 factorial part. After 20 derivatives, we'll have knocked it down to a constant term. We brought the 20 down in the first derivative, 19 in the second, 18 and so forth. And on the 20th derivative, we brought the 1 down, and we were just left with the constant. 17x to the 15th, what's going to happen with that? It's going to be 0. Because what happens is, by the time you hit the 15th derivative, you're going to have 17 times a big number, which is 15 factorial. But then it's a constant. So at the 16th derivative, it goes away. That definitely went away. The sign, that one's going to be the interesting one. So first off, there's a power, we have 3 to the 20th. Now we have to figure out, this is a pattern that repeats every 4. I've taken 20 derivatives. So where am I at in the pattern if I repeat every 4?
Positive sign.
I'm back to positive sign. Because every 4 I've reset. So this would be positive sine of 3x. Okay, so that's the 20th derivative. Now, what about the 35th derivative? Well, let's talk about the 35th derivative at x. And then we plug in 0. 3 to what power? 35. E to the 3x. The x to the 20th is gone. 17x to the 15th, gone. That's gone. Okay. Then we have the sine 3x. Now, 35 derivatives, we're also going to have 3 to the 35. But where are we at when we've taken 35 derivatives? Where are we at in our cycle? So this is at 0, 1, 2, 3. Now, why do I pause dramatically at 3? Well, it turns out, true story, 35 is equal to 32 plus 3. You're like, whoa. They never taught me that. No, they did. But why is that special? Well, 32 is a multiple of 4. So what I really want to do is I want to say, how many multiples of 4 did you get? Okay, I don't care about that. I care about, at the end, where did you end up? So it's like I went and cycled through 8 times, and then on the last pass, I got 3 steps. Now, if you know fancy words, this is sometimes called modular arithmetic. But okay, so that says we're at this piece. So minus, and then it's a cosine. Now, that's not our answer because that's just the function. We want it at 0. So the 35th derivative at 0 would be 3 to the power 35 times e to the 0 minus 3 to the power 35 times cosine of 0, which becomes e to the 0 is 1, cosine of 0 is cosine of 0 is 1. So you get 3 to the 35 minus 3 to the 35, which tells you that the answer is 0.
So in the second one where it's f to the 35 one, why does the factorial thing disappear?
Well, because the factorial is not a function of x. See how there's no x involved? So it's a number. 20 factorial it's a huge, huge number. But it's a number. And so once you take a derivative of a number, a constant, that goes to 0. So that's why it disappears.
But why didn't you do that? Like, why did you write it in the first one, and then why did you write it for f to the 20, and then in the second one you didn't?
Well, because what was happening, so why is this 20 factorial showing up here and not there? Because you have this polynomial, x to the 20th here, and if you have a polynomial, it takes a while for it to go down. Because every time you take a derivative, you're knocking the power down by 1. So you started with x to the 20th, then x to the 19th, then x to the 18th. And so if you start with something with x to the 20th, by the time you hit the 20th derivative, you're down to a constant. So you're still present, and that's where that's coming from. But as soon as you hit the constant, at the next step, you're free, and it's gone. And so what happened was, it turned out that at 20 derivatives, that x to 20th was still kind of lingering on, and then it finally said, all right, I give up. I'm out of here.
So as soon as it passes 20, then it's no longer.
That's correct, yeah. So if you have x to a power, a whole number, like if you have a fractional power, it's always going to be there and to be very annoying. But if it's like x to 100, after 100 derivatives, so 101st derivative, then it's gone. But before that point, there's still something there. It's just depending on how far you've gone as to what that something is. All right, good. Rounding the corner. We're near the end. Number 10. So, here's this function, f of x, shown in the picture below. Determine the limit as x approaches 1 of f of f of f of x, or show the limit does not exist. Well, we don't actually have the function explicitly. So, what do you notice about this function? Well, you have a picture, but we have kind of a name for functions that look like this. And I know that's very vague to say we have a name. You're probably thinking like unpleasant. Ugly sounds aggressive. Well, let's. Yeah. Okay. All right. I think it has a certain charm, but I would call this is something I would call piecewise, which is whenever you see it, there's little pieces to it. We've encountered piecewise functions before. So in other words, the behavior in the different parts is behaving differently. Now, when you're dealing with piecewise functions and you have limits involved, what's the way to handle it? Or maybe better yet, we can't sketch what f of f of f of x looks like. So, what can we do? Well, here's the key idea on this particular problem. We will look at this and break it into one-sided limits. F of x as we approach from above, and what happens as we approach from below. So oftentimes if you have something where it's not so clear what's going on, you say, okay, let's just break and say what happens as I come in from one side. You channel your inner mathematician and you go something like from the right, as we approach one, what happens from the right, and then you go round two. From the left, what happens as we approach one from the left? Yes? Okay, you don't have to do that, but you can imagine that you do that. All right, so here we go. Now, I'm just going to work on this. In some sense, you might think that this is a problem that you can think of as kind of like an onion problem, because it has layers. And also, there might be a few tears shed by the time we reach the end. But we're just going to start, and you start from the inside. So, currently, what's happening to x? What is that doing?
Approaching 1 from the right.
Yeah, it approaches 1 from the right, which you can also think of as it approaches 1 from above. Okay? So, I'm approaching 1 from above. What's happening to the function? What is it doing? It's going to what? So I'm approaching 1 from above, which means I'm doing this. What's the function approaching? It approaches 2. From which direction does it approach 2? See how it's coming up into 2? So am I below 2 or above 2 as I approach? Below. So now in the first layer, this says you're approaching 2 from below. Okay, so now we approach 2 from below. As we approach 2 from below, what do we approach? We approach 4. From which direction? Approaching 4 from above. So now, this is approaching 4 from above. Now, we're ready for our next layer, our third layer, which, by the way, is also our last layer. As we approach 4 from above, what are we approaching? We're approaching 3. From which direction? Approaching 3 from above. So what's the limit do here? Well, as we approach 1 from above, we work it through and it says, hey, you're really approaching 3. Okay, so that's that side. Now, do we know what the limit is?
No.
Not yet. If there's an answer, it's either 3 or does not exist. But we don't know for sure which one because we also have to compare what happens here. So, let's compare. Okay, so now we're, 1 from below. So, what's the inner layer doing? As we approach 1 from below, what do we approach? 4 from below. So, 1 from below. Next layer, we approach 4 from below. Okay, as we approach 4 from below, what happens? We approach 2 from above. All right, so here's the x. Here's f of x. Here's f of x. So, what happens as we approach 2 from above? We approach 3. And from which direction? From above. Okay, which means this is 3. So, from the left and from the right, we both got 3. What's our conclusion? So since these match, then the limit, as x approaches 1, of f of f of f of x equals 3. Ah, what a fun problem. What a fun problem. But really, this is just testing. Do you understand how things are approaching? Yes?
For this type of problem, how we have to show in the exam, like what are the points, like for the first question, if we don't write the limit, we lose some points. So what are the things that we need to show in this type of problem?
Well, usually on this type of problem, there's like 4 or 5 parts. And then this is just like the 5th part. And basically what we'd be looking for is, did you write that? Did you get 3 on both? And did you say that the limit was 3? But again, this would probably be like worth 3 points. And then there's be other questions like, what's the derivative at, find the f prime of, or what is it, 7 halves. We can do that. Like, oh, okay, f prime is 7 halves. Because essentially what happens is there's a couple ways we can give you functions. We can give you a table of data. We can give you pictures. We can give you explicit functions. And so you want to be flexible. You want to be able to say, look, whatever you give me a function. Hey, I love functions. I'll do whatever you want me to do to that function. Just tell me what to do. Or I have a picture. It's like, okay, I'll use the picture. But yeah, normally we probably wouldn't have a whole problem just be this. This would just be the fun icing on the cake. Part D. These are fun. Okay. Number 11. All right. So number 11. Find the derivatives for the following functions. Okay. So this is just saying, hey, let's take derivatives. So a good chance for us to practice our rules. So we're going to have lots and lots of rules. So you want to be really careful and really comfortable with all your rules. And I think students kind of like these problems because they're sort of like, hey, I know my rules. So let's just let's start with part A. Part A, g of x. Well, let's go through our rules. Derivative of x to the 7/4. What would that be?
That'll be 7/4 x.
7/4 comes down. X to what power?
5/4.
5/4? 6/4? 3/4? Yeah, it's 3/4. Yeah, so be careful. It's, subtract 1. So if you have 7/4 and you subtract 1, that's like subtracting 4/4. Okay, sine. What's the derivative of sine? Cosine. All right. Now there's a 2x on the inside. Do we need to do anything about that 2x? What do we do with it? Chain rule, so we need to put a 2 in front. Secant. All right, do we know our derivatives for secant?
Tangent of x, secant of x.
Okay, derivative of secant is secant and tangent. So we have a secant. Is it plus or minus, by the way? The inside stays the same. Do we need anything else? 3. Need a 3. Now, you might say, well, wait a second. I see a secant and tangent. Maybe I should put a 9. No. Just 1 3. Okay. And the derivative of e to the x? E to the x. Yes. Good. All right. So that one's not so bad. Really, that was a very straightforward. It's like, okay, here's a function. Maybe just some really light playing around with the chain rule. Okay, so there's part A. Now part B, we spice things up. You have a cosine y over e to the y and y squared tangent of y. Now there's a couple ways you could handle the first part. So let's talk about it and make a decision. Cosine y over e to the y, what's one way we could take that derivative? Quotient rule. Is there another way we could take that derivative? Well, it's not a chain rule because it's not like e to the y is on the inside of anything. Well, maybe. You can think of this, though, as cosine of y times e to the minus y. So in the sense that you can think of this as e to the y to the negative 1, you can think of it as a chain rule. But it's also, oftentimes you can change a quotient into a product. It just depends what you like doing. I tend to like it, if it's simple enough, I would probably go and rewrite it in the way that's written there, in the somewhat purplish color. You still get the same answer. So sometimes there's a little bit of flexibility in terms of how you take derivatives. So let's take the derivative. Now notice the first time the variable was x, we had no problem. Now the variable is y. Is that going to change anything? No. It's the same process. The biggest change is instead of writing x's, you're going to write y's. So they're just symbols. No problems. All right. H prime of y. Okay, so looks like we have some product rules being tested. Derivative of cosine? Negative sine. So negative sine y. Then we write down the e to the minus y. And now we have cosine y times the derivative of e to the minus y. Derivative of e to the minus y? Yeah, because you're going to get a negative coming down by the chain rule. So what will happen is you have a cosine of y, because the function stays alone, and then derivative of e to the minus y is e to the minus y, and a minus comes down. So I'm going to put a minus there. So this minus becomes from the chain rule. Next term, derivative of y squared, 2y. The tangent, leave it alone, because that's what the product rule says. Everybody gets its turn. Plus y squared times the derivative of tangent, which is secant squared. And now we're done. So, by the way, you should be comfortable with all the functions that you see here, namely x to a power, e to the x, sine, cosine, secant, tangent. These are your basic building blocks. You should know all of these functions and know how to deal with them. Okay, so now that we've had the warm-up, it's time for the main event. And I know this looks like K. It's actually kappa. But if you like, you can say it's K. Between us, we'll say it's K. We're all friends here. Okay, so what are some rules that we're going to get to do here? Before we start, let's think about all the rules we get to do.
Many chains.
There's definitely some chain rules going on. What else do we get? Yeah, I think this is definitely a quotient rule. Yeah, I just don't think there's any advantage to not doing the quotient. Anything else going on? So we've mentioned chain rule. We've mentioned quotient rule.
looks like there's a product rule at the bottom.
There's a product rule that's going to come into play. Oh yeah. There's a sum rule coming in here as well. Every rule. It's like all the rules are here. And it's all the this one is like, if you can take this derivative, then okay, good. We can take that derivative. All right. Well, now we're just patient. You know, these are, you have to think about what layer we're on. Because I like to think about this as thinking about, all right, sort of what's the current rule in place. So for example, what's sort of the big overarching rule that we're using? Yeah, the big rule is we have the quotient rule. And now we're going to say, okay, so we're going to think of the quotient rule. We have a part over a part. So the quotient rule says you take low d high, right? So we're going to take the bottom. So that's good news for us. We don't have to take that derivative yet. By the way, the square root, just in anticipation, I'm going to write this as t cubed plus cosine of t to the 1/2. Writing things to the square roots as a half, that's a very calculus thing to do, because calculus is much more comfortable with a 1/2 exponent than it is with the square root symbol. Now we're going to times the derivative of the top. All right, derivative of sine. It's cosine. The inside, what do we write down? Yeah, the t plus 5 e to the t squared. You leave the inside alone for right now, but then what do you do? Multiply by derivative, which is 1 plus
5e to the 2t.
Be careful. Derivative of 5e to the t squared. So we're just be what? Someone said 10. Anything else?
Is it t squared? 5e t squared.
Well, okay, so let's think about it. There's the 5. Yeah, just this is the thing, is it's easy to get lost. So we're just sort of focusing on, okay, so right now we're trying to say what's derivative of this piece. And now we don't need to worry about all this other part that's going on. So we say, okay, my focus right now is what's the derivative of t plus 5e to the t squared? The derivative of t is 1. Okay, that's good. I can handle that. Derivative of 5e to the t squared. The 5 is going to stay. E to the t squared, what rule do we need for the derivative of e to the t squared? Chain rule. So the derivative of e to the t squared would be e to the t squared, because the derivative of e to anything is e to the anything. And then we need also a 2t. So there will be a 5e to t squared times another 2t, and if you put that together, you get 10t, e to the t squared. All right. I'm already regretting how small I've written this. Okay. Bottom times root of the top minus, so this is all still the numerator. I hope it fits. So bottom times root of the top minus the top, sine of t plus 5et squared times the derivative of the bottom. Okay. Well, now we're to the stage we're taking the derivative of the bottom. What rule do we need?
Product and chain.
Yeah, so our big rule, our first layer is t squared, because the onions, like what's our layers? So the first layer is the t squared. So you say, okay, let's say we'll take the derivative of the first term, 2t times the second, sine of t cubed plus cosine of t to the 1/2. So derivative of the first times the second plus the first times the derivative of the second. Now, the derivative of derivative of sine of this expression. Well, chain rule, derivative of sine is cosine. The inside, you leave it alone. That's the chain rule. But then what do you do? Well, there is an over the bottom squared, but we're not there yet. There's a lot of space here, suspiciously much space. which I feel like we're going to fill up and probably not even have enough space for what's about to come. So remember, we're at the point where we're taking the derivative of this part, the sine of the square root of t cubed plus cosine t. And we said, okay, derivative of sine is cosine, and we left the inside alone, and then what happens?
Multiply that by the derivative of that.
Now we've got to multiply the derivative of the inside. Okay, so notice the inside is something to the 1/2 power. So what comes next? The 1/2 comes down. And then it'll be t cubed plus cosine of t to what power? Negative 1/2. So what we had is we had that, if you look at what we have here is we have sine, and inside sine is square root, and inside square root is this t cubed plus cosine t. So it's like a function in a function in a function. It's the turducken of functions. Just these nested things going on. All right, now are we done? No. Not because we're missing stuff out the bottom squared. What else do we need to write down? Well, what?
You have to take the derivative.
Yeah.
Minus sine of t.
Yeah, so we have to keep working our way in. So derivative of t cubed is 3t squared, and derivative of cosine is minus sine. Now, are we done here with the top?
Yes.
Yeah, I hope so, because we don't have any room left. And yes, we are in fact done. We've gone through all our oniony layers. And of course, downstairs, it's t squared sine square root of t cubed plus cosine t squared. And that is the derivative. That's it. It kind of flows naturally, right? Well, maybe not. So how do you get it to work? Just sort of don't be overwhelmed. Just think, okay, what's the current rule? Because the way I oftentimes look at these things is I see sort of like, okay, there's the outermost layer is the quotient, then upstairs there's a chain rule, and then inside there, that's all simple. Downstairs, there's a product rule. The first one, easy. Next one, okay, chain rule, inside a chain rule, and then the inside piece is okay. And it's just work through it patiently. What's the current rule? Don't be overwhelmed. Don't be like, oh, it's taking a lot of space. Be like, it's okay. Sometimes these things take time. All right, which brings us to number 12. Our last problem for today. Man, it feels like we just started too. So find values a, b, and c so that the following function is differentiable at t equals 1. And then we have the function listed there. h of t, which is 2t squared plus at minus 5 divided by t minus 1. And that's if t is below 1. And bt squared plus ct if t is above 1. Now notice it says the word differentiable. Now if I want to be differentiable at a point, what needs to be true? To be differentiable at a point. I definitely need to be continuous. And what does it mean to be continuous? Continuous says that the limit as I approach, in this case it's 1, it could be just any point. The limit as t goes to 1 of h of t has to equal h of 1. So that has to absolutely be true. Now that just makes sure that things line up. So in other words, they come together. But just because things come together doesn't mean it's differentiable. What else do I need to make sure?
The derivatives of both sides have to be the same.
Yeah, and then the derivatives from both sides have to match. So these are two requirements that must be true. Okay, so that's what we have to satisfy. All right, so let us begin. This will be fun. Let's start perhaps below 1. Let's see what we can say. So because this is piecewise, and really it's not surprising that it wants us to say what's happening at 1, because that's where we might run into troubles. So what's happening at 1? Well, let's approach 1 from below. So the limit as we approach 1 from below of h of t, that's the limit as we approach 1 from below of 2 times t squared plus at minus 5 over t minus 1. Now, when you have a limit, what's the first thing you should do? Plug in the number. You should always just say, what's happening at my number? Because if it's nice, it's like, okay, I'm done. Life was good. And if it's not nice, then it's like, okay, I get to do more work. So we plug in 1. What do we get? Well, downstairs, when you plug in 1, what do you end up with? You end up with 0. Upstairs, what do you get? You get 2 plus a minus 5, which becomes a minus 3. Yes? 2 minus 5, negative 3. Now, at this point, you're probably thinking, I'm dividing by 0. But this is good information for us. The fact that I'm dividing by 0, what does that tell us about a minus 3? It has to be 0. If a minus 3 is any number other than 0, what's happening is that the function is going to blow up. There's going to be an asymptote. So, a has to equal 3. Cool. So I'll actually make a list over here. A equals 3. So a equals 3 for limit to exist. Now, unfortunately, that's not enough to say what the limit is, but it does say what a has to be. So now let's update. So I can update. I'll put a little 3 there. Let's think about this function. 2t squared plus 3t minus 5 over t minus 1. Now what's going to happen is that it's going to go to 0 over 0. I'm not taking the limit right now. I'm just thinking about the function. What do we know about the numerator? Or at least what do we want to be true about the numerator? What would be lovely? Well, it would be nice if it factored, right? Because it's polynomial. We want things to factor. My question to you is, does it factor? And do we know one of the factors for free? Yeah, we know it factors because now we've chosen a equals 3, that says when you plug in 1, you're going to get 0 out, which means that 1 is a root. So if 1 is a root, it has to have t minus 1 as a factor. So what's the other factor going to look like?
T plus 5.
2t plus 5. Where does that come from? Well, notice you got to get up to 2t squared. So I have t, and so what do I have to multiply t by? I get up to 2t squared. The answer is 2t. I have minus 5. Here's minus 1. What do I have to multiply minus 1 by to get to minus 5? And the answer is plus 5. Now the t minus 1s I can cancel, and I'm okay with that because t is actually below 1. So now, lo and behold, our function becomes really a lot simpler. It's the function 2t plus 5 if we're below 1, and then it's bt squared plus ct if we're above 1. Okay, so now life has become slightly simpler. Now we're not done yet. Let's figure out, we still have to do continuity. So let's go back and do our one-sided limit. So now, as we approach 1 from below of h of t, we say, hey, that's a lot simpler now. That's really limit as we approach of 2t plus 5. And what does that approach? Goes to 7. Then we have the limit as t approaches 1 from above of h of t, which is the limit as t approaches 1 from above of b times t squared plus c times t. And what does that approach? Well, it approaches b plus c. But it has to be 7, because they have to match. So one thing we can conclude is that b plus c equals 7. That's from making sure that it's continuous. So remember, if you see what does it mean to be continuous, the limit has to agree with the function. Okay. We also need to have the derivatives from both sides matched. So let's take a look at the derivatives. So the nice thing is if you have a piecewise function, you can do piecewise derivatives. Derivative of 2t plus 5? 2. And that's if we're below 1. Derivative of b times t squared plus c times t.
That'll be 2bt plus c.
2bt plus c. And that's if we're above 1. I'm gonna hold off and not include 1 just because I haven't actually made things line up yet. So now we do the same process. What happens as we approach 1 from below of h prime of t? Well, that's what happens as we approach 1 from below of 2. What does 2 approach as you go towards 1? 2 goes towards? Yeah, 2 goes towards 2. That's correct. Yes. So 2 goes to 2. And from above, limit as t approaches 1 from above of h prime of t. That's the limit as t approaches 1 from above. Because now I can plug in what I am of 2 times b times t plus c, which approaches well, approaches 2b plus c, but that has to match with 2. Now, at this stage, we're like, we can say that b plus c has to equal 7, because it says b plus c equals 7, and that 2 times b plus c has to equal 2. So now we have 2 equations and 2 things we don't know. But that's a good number. And you're probably thinking, boy, we see these a lot. Yes, you do. We love these problems. I like to look for ways to add and subtract, combine functions together, a nice way to cancel stuff. In this case, if we subtract, so if I take the left-hand side, it's 2b plus c, subtract b plus c, what am I left with? B. On the other side, 2 minus 7? Negative 5. So b will be negative 5. All right, now that I know b, I can plug it in. So for instance, negative 5 plus c has to equal 7. So what should c be?
12.
C should be 12. So our answer is a should be 3, b should be negative 5, and c should be 12. That's what will make the function differentiable at t equals 1. And that was our last problem. See, there's no more. It's all blank. So thank you for coming. Good luck on the test. If you can do what we've talked about today, you're going to be in great shape. If you can do what we talked about today and check the reviews and the quiz problems, you're going to be in amazing shape. And you're going to walk in confident that you'll do okay. And maybe even better than okay. So have a good day.